In some of our previous lessons, we discussed performing different operations on polynomials, including division. As we saw in those lessons, the division of two polynomials doesn't always produce a new polynomial, but it does create a very important function known as a rational function. Basically, a rational function is just a ratio of two polynomial functions. So it's one polynomial divided by another polynomial. And notice how ratio is the first 5 letters in the word rational. So that's where the name comes from. So for example, f of x equals x squared plus 1 divided by x squared minus 1 is a rational function. And so are g of x equals x plus 2 divided by x cubed plus 3x squared plus 3x plus 1, and h of x equals x to the 5th plus 4x divided by x to the 4th plus 1. In the next few lessons, our focus will be on these rational functions. And in this lesson, I'd like to study two properties of rational functions: their domains and their graphs. You and I have talked about domains and graphs throughout this course. In fact, we talked about domains and graphs of radical functions in the previous lesson. Let's start the conversation in this lesson by talking about domains, which will play a role when we get ready to talk about graphs in just a minute. Now, several lessons ago, I shared with you that the domain of any polynomial function is the set of all real numbers. In other words, a polynomial has no forbidden numbers for its domain. We can plug anything or any real number into a polynomial function. So maybe, just maybe, it's true that the domain of every rational function is also the set of all real numbers, since, after all, rational functions are built directly from polynomials. Well, it turns out that that's almost true, but only almost true, except for one thing: division by zero. And you and I both know that you just can't divide by zero. So let me show you a quick example looking at the domain and walk through the kinds of things you have to watch for when you're trying to find the domain of a rational function. Here's the example. Determine the domain of the function f of x equals x squared minus 4 over x squared minus 1. Now notice that really is a rational function. It's a polynomial divided by another polynomial. So we're in the right ballpark. The first thing that you and I should do with one of these kinds of problems is factor the numerator and the denominator of the function. Now in this example, since it's our first, I've chosen two pretty easy polynomials here, both of which are differences of two squares. So f of x, our original function, can also be written as f of x equals x minus 2 times x plus 2, all divided by x minus 1 times x plus 1. Now next, notice what happens if you try to plug in x equals 1. The numerator is perfectly fine. It becomes negative 1 times 3, which equals negative 3. But the numerator is not the important thing here. Remember, it's that division by zero that we're trying to avoid. And that means you've got to look in the denominator, not the numerator. If you plug in 1 in the denominator, you're going to get 0 times 2, which is 0. That gives us division by 0, and that's a no-no. So here's what we know. We know that x equals 1 cannot be in the domain of this function f of x. Now, are there any other values which are not allowed in the domain of this function? Sure. X equals negative 1 is the other value that's not allowed in the domain, and that's because of the factor x plus 1 that was in the denominator once we factored our function. And this leads us to the rule of thumb for how to find the domain of any rational function. This is exactly what you should do every time you have to find the domain of a rational function. Let f of x be p of x over q of x, where p of x and q of x are polynomials. That means f of x will be a rational function. Then the domain of f of x is the set of all real numbers except for the values of x where q of x equals 0. That's the set of values of x where the denominator is going to equal 0, and that's the values that will cause that division by 0. So in the example I just completed, p of x was x minus 2 times x plus 2, and q of x was x minus 1 times x plus 1. And the values that we couldn't allow in the domain of the rational function were x equals 1 and x equals negative 1, because these were the two values of x where q of x equals 0. So let me emphasize one more point here before we go on to the next domain example. We really do not care about the numerator of a rational function when we're looking at the domain of a rational function. The numerator will be extremely important when we get ready to draw the graph. But for finding the domain, the only thing we should look at, the only thing we should focus on is the denominator. So make sure that's what you look at first when you get ready to find the domain of any rational function. Now, hopefully you've got an idea of what we're doing here, so let's move to a second example, and I'll suggest you try this first and see how you do. Find the domain of the rational function f of x equals x squared minus 6x plus 5, all divided by x cubed minus x squared. Okay, now as before, we should start by factoring both the numerator and the denominator of the function. And when we do that, in this case, you're going to get f of x equals x minus 5 times x minus 1 divided by x squared times x minus 1. Okay, now there's a very important point to make, so listen really carefully. In this example, there are two values of x that we cannot allow into the domain of this function. They are x equals 0, which comes out of the fact that you've got that x squared term in the denominator, and x equals 1, which comes from the fact that you have that x minus 1 term in the denominator. You are not allowed to have 0 and 1 in the denominator. You're not allowed to have 0 and 1 in the domain. Every other value is okay. Now, some students might say, wait a minute, I can cancel an x minus 1 from both the numerator and the denominator and rewrite the function as x minus 5 divided by x squared. Well, let me be clear. That cancellation is fabulous. And the rule that you now have written down for f of x, which is x minus 5 over x squared, is allowed to be simplified in that way. But the fact of the matter remains, the domain of the original function f of x, which is what you and I were trying to find, does not allow x equals 1 to be included. Bottom line, if you or I tries to plug in x equals 1 into the original function, we're going to get 0 divided by 0, and that makes absolutely no sense mathematically. So the idea here is this. When you're looking for the domain of a rational function, only focus on the denominator. Once you have the domain written down and you've remembered which numbers are not going to be allowed in the domain, then go ahead and do the algebraic simplification, like canceling terms out of the numerator and denominator, in order to make the function look simpler as a rule. But do the domain first before you do any of that cancellation. Write that domain down and don't lose it. All right, now let's transition to some graphing now. We've talked about domains for several minutes, and we now hopefully understand how it is we find the domain of a rational function. Now I want to talk about actually graphing rational functions. And it turns out there are a lot of different things that you want to do, or a lot of different tools that you want to use that will help you when sketching the graph of a rational function. Let me just briefly mention what some of those tools are. Do you want to find the x-intercepts if the graph has any x-intercepts? And actually the y-intercept if it also has such a thing. You might also want to look for what are called vertical asymptotes and horizontal asymptotes. And both of these are straight lines. Vertical asymptotes are vertical straight lines. Horizontal asymptotes are horizontal lines, which serve as boundary values, if you will, or walls over which the graph on its ends, either out in the left and right side or top and bottom, cannot cross, cannot touch. We talked a bit about asymptotes when we dealt with certain conic sections several lessons ago. Those kinds of lines which serve as boundaries are going to come into play again as we graph rational functions. Okay, so let's look at the following example and try to bring all these tools in to help us sketch the graph. Sketch the graph of the function y equals 4 divided by x plus 3. Now, let's start collecting all this information before we try to sketch the graph. First, what's the domain? You should always ask that first. In this case, it's pretty easy to see because I've given us a pretty friendly function. It's not very messy, if you will. And in this case, the only value of x which is bad to plug in is x equals -3. -3 for x would cause division by 0. So my domain is the set of all real numbers except x equals -3. Okay. Next, let's look for x-intercepts. Now, you're not guaranteed that there will be x-intercepts, but let's look for them here. And here's an important rule of thumb to find x-intercepts. When you're looking for x-intercepts of a rational function, p of x over q of x, we need to find the zeros of the numerator polynomial p of x. So what you do to find x-intercepts is you always set the numerator equal to 0 and then solve for x. And those values of x, which make the numerator equal to 0, will be your x-intercept values. Well, in this example, all you're going to set equal to 0 then is 4, because the numerator is equal to 4. So you're looking at the equation 4 equals 0. Well, is that ever true at all? Absolutely not. There are no values of x which are going to make 4 equal to 0. So that means in this example, there are no x-intercepts for the graph. It's never going to cross the x-axis. Now you might say to me, well, that wasn't helpful. X-intercepts would have been really nice to have. Well, the fact that it never crosses the x-axis is a piece of information. So when you get ready to draw this graph in a moment, you now know that it can never cross the x-axis. Part of it might be above and part of it might be below, but you're never allowed to actually touch it. Okay, now, can we find the y-intercept? Well, how do you find the y-intercept? Remember now, you've got to keep all these tools straight, so you're going to want to remember them very carefully. The y-intercept is going to be the point where x equals 0, right? Because if you're on the y-axis, you're a point of the form 0, comma, something. So to find the y-intercept, you simply go to the function and plug 0 in for x everywhere that you see x. That actually makes finding the y-intercept relatively straightforward. In this case, you're going to plug 0 in for x, and you're going to have y equals 4 over 0 plus 3, because you've plugged 0 in for the x, and that means y equals 4/3. So the y-intercept in this example is pretty straightforward. It's the point 0, comma, 4/3. Now, if you've got a piece of graph paper in front of you and you've drawn your x and y axes, you can actually plot that point now, 0, comma, 4/3, and now you have a point on this graph. Now, let's look next for vertical asymptotes. Now, what are those vertical asymptotes again? They're going to be vertical lines, so they're going to have an equation like x equals a constant, like x equals c, and that is going to be a line which serves as a boundary for the graph. Moreover, as the values of x get really, really close to c, the values of the function are going to grow huge, either in the positive infinity direction or the negative infinity direction. So in this example, there's going to be one vertical asymptote, and it's going to occur at the line x equals -3. Remember that -3 was a bad guy. I couldn't plug it in for x because it was going to cause division by 0. Now, what happens if I plug in a number close to -3 for the value of x in the function? Say, for example, we plug in something like x equals -3.0000001. Now, that's really close to x equals -3. And if you think about it on the x-axis, it's actually just a little bit to the left of x equals -3. Well, when you plug that into the function, you're going to have y equals 4 divided by negative 3.00000001 plus 3. And now look at that denominator for just a second. Those two pieces, the negative 3.00000001 plus the 3, will actually, the 3's will go away, and all you'll be left with is, in the denominator, negative 0.000001. Now when you divide 4 by that really tiny denominator, what do you get? Well, you get a very large number. 4 divided by that small number is going to give you a 4 followed by what appears to be 7 zeros. And it's also negative because you have the negative in front of the denominator number. So what has happened? The y value is an extremely large negative number. So when I plugged in x equals negative 3.00000001, the y value is really large, but it's negative, so it's going way down. And that means, since this point is close to this vertical asymptote x equals negative 3, the graph just to the left of that vertical asymptote is trying to go down very, very fast, and it's going down to negative infinity. Okay, now let's try another value, but this time just a little bit to the right of that vertical asymptote at x equals negative 3. Now just to the right of that would be something like negative 2.9999999. Okay, now if you plug that value in for x into that denominator of the function, you're going to have y equals 4 divided by negative 2.9999999 plus 3. And look at that denominator for a second. That's going to become positive, first of all, because the 3 is slightly larger than the negative 2.999 and so on. And that denominator becomes 0.00, a whole bunch of zeros with a 1 at the end. 4 divided by that is going to become a very large number. When you divide 4 by a tiny number, it's going to become a huge number. And in this case now, because that denominator is positive and the 4 is positive, it turns out you have a very big positive y value. So when the x was just barely to the right of that vertical asymptote, the y value is huge and it's positive. And that means that to the right of this vertical asymptote, the graph is going to go upwards into the positive infinity direction and get extremely close to that vertical asymptote. So now I know that around that vertical asymptote, this side of the graph is taking off like this, and the other side is going down in the negative infinity direction. Now, we'll point that out again when we actually draw the graph, but that's an important bit of information that you need to have in mind. And keep one other thing in mind. The vertical asymptote that I've been talking about, this sort of boundary line, is not actually part of the graph. So if you really wanted to be technical about it, you wouldn't even draw that vertical asymptote in because it's not part of the graph. Some people even like to draw their vertical asymptotes with a dashed line. Remember when we were talking about hyperbolas, we did the same thing to remind them that that asymptote is actually not part of the function's graph. It's simply acting as a natural border or a wall that doesn't allow the graph to pass. Now, they're really important, these vertical asymptotes, so I do suggest you draw them in, but if you want to try to remember how to keep them from being part of the graph, you might want to draw them in with a dotted line or a dashed line instead of something that's nice and solid. Now, you might be asking me, what if in general I wanted to find vertical asymptotes, not just for this one example? Where would I look to even find those vertical asymptotes? Well, you always want to look, when you're looking for vertical asymptotes, for the values of x where the denominator of the function equals 0. But that's only after you've done the cancellation that's possible in the rational function. So, vertical asymptotes are going to occur at values of x where the denominator equals 0 after you've already canceled any pieces of the rational function that you're able to cancel. Okay, the next thing we should look for is horizontal asymptotes. A horizontal asymptote is a horizontal line that the graph of the function is going to get close to at the ends of the graph on the left and on the right side of the graph. To find a horizontal asymptote, We want to keep the most powerful term or the dominant term in the numerator of the function and in the denominator of the function. And we look at just the ratio of that dominant term in the numerator divided by the dominant term in the denominator. In this case, you're basically just looking at the 4 on top. It's the only term up there. And the dominant term in the denominator is the x. The x would grow a lot faster than a 3 because a 3 is just a 3 and it's always just a 3. So what we do is we look at the ratio 4 over x. And then we ask ourselves this question. What if the x was allowed to get huge? Like what if you plugged in x equals 1 million or 1 billion even? At that point, you would have 4 over a million, and I hope you realize that that's really small as a fraction. In fact, as the x gets bigger and bigger and bigger, that ratio 4 over x is going to go to 0. And that tells you that as the x values get large and in the positive direction, the y values of this function are going to get very close to the line y equals 0. Now you also need, if you want to do horizontal asymptotes correctly, you should also ask yourself, what happens when I let x get large in the negative direction? In other words, what if I plugged in negative 1 million to this little ratio 4 over x? If I plug in a negative 1 million, I'll have 4 over negative 1 million, which still, by the way, is very close to 0. It is negative, but it's still tiny. And so even on this side, we know that the graph is also getting very, very close to the line y equals 0, because 4 over 1 million and 4 over negative 1 million are both very close to 0. So this graph is now taking shape. I now know it has no x-intercepts. I know it has one y-intercept, which I've already found. It has this one vertical asymptote at x equals negative 3. I know the way that the pieces of the graph try to behave around that on both sides. And I know that I have this horizontal asymptote at y equals 0. Now I would just suggest we plot a few more points and connect the dots, keeping in mind all the information I just shared. Okay? So let's plug in a few values of x, draw in those points, and connect the dots based on what we know about these asymptotes and about these intercepts. So if we plug in some of that point information, if you will, you're going to have the following kind of thing for your graph. If you let x be negative 6, for example, then y is going to be negative 4/3. If you let x equal negative 5, then y is negative 2. When x is negative 4, y is negative 4. When x is negative 2, y is 4. Notice I just hopped over x equals negative 3. Remember, I'm not allowed to plug that in. When x is negative 1, I would get 2 back for y. When x is 0, I get 4/3. We already knew that because that's the y-intercept. Now plot all those points, connect the dots, and keep all this asymptote information in mind, and the graph you'll have will then look like this. And notice the vertical asymptote, the horizontal asymptote, the y-intercept, and the lack of those x-intercepts. And that graph is good to go. Okay, here's one for you to try. Let's be sure to factor wherever you can first before you jump right into the problem. Sketch the graph of y equals x squared minus 1 divided by x squared minus 4. Okay, after factoring, we're going to have y equals x minus 1 times x plus 1 divided by x minus 2 times x plus 2. And notice that there are no cancellations there, so that's fine. Remember also that the domain will be the set of all numbers x other than 2 and negative 2. 2 and negative 2 are going to cause division by 0. Now let's start getting this information like we did in the previous example. The x-intercepts, I need to worry about where the numerator equals 0. So that's when x minus 1 times x plus 1 equals 0. And the two values of x that are going to make that true are x equals 1 and x equals negative 1. So 1 comma 0 and negative 1 comma 0 are the x-intercepts. In fact, if you want, you can plot those right now on your graph just to get you started. Now the y-intercept. Now you're going to plug 0 in for x and see what you get back. If you go back to the original version of the function, which you don't have to do, but if you go back to that and plug 0 in for x, you'll have y equals 0 squared minus 1 over 0 squared minus 4, which is negative 1 over negative 4, which is 1/4. So the y-intercept is at 0 comma 1/4. You can plot that point now as well if you want. Now, vertical asymptotes. Well, now you look at when the denominator equals 0, x minus 2 times x plus 2 equals 0, and the two values of x that are going to cause those vertical asymptotes to occur will be at x equals 2 and x equals negative 2. So those are the equations of those two vertical asymptotes. And now you need to do some work to ask yourself what happens on either side of those two vertical asymptotes. If you look at the vertical asymptote at x equals 2, you should ask yourself, what happens if I plug in 2.01 for x or 1.99999 for x? Those would be values on either side of that vertical asymptote, and depending on whether those y values were positive or negative, you would know whether the branch of the graph is going to go up next to that vertical asymptote or down. So you need to do that for each of those two vertical asymptotes, and in a minute when we draw the graph, you'll actually see how those behave. Okay, now let's look at the horizontal asymptote. And now here, remember what you have to do is keep the highest power term on top, or what I call the dominant term on top, and the dominant term on the bottom, and sort of throw away the other terms for a few moments. And in that case, it's just x squared over x squared, which is 1. And that tells you that the horizontal asymptote is at the line y equals 1. Now remember, the vertical asymptote and the horizontal asymptote are not actually part of the graph. They're just acting like boundaries, but they're still helpful to have, so you might as well draw them in maybe with dashed lines. Now you draw in all these pieces, and you plot a few more points. Maybe you plug in x equals things like -6, -5, -4, maybe -3, 3, 4, 5, and 6, something like this, and plot all the points that you get from plugging those in. You'll probably want to use a calculator if you'd like to get the y values there. And with everything you have at that point, you have this graph. You can actually draw it at that point. And by the way, notice that there's actually an upside down U piece in the sort of middle of this graph, so to speak, between the two vertical asymptotes. How would you have known that that was there? Well, to be honest, you might have had to plot several points in between those two vertical asymptotes, between those values at which those occurred, just to see that it really was that U shape. There's nothing wrong with plotting a few extra points and then connecting the dots. Now, before we jump to the next example, let me just remind you, don't connect the dots over those vertical asymptotes. If there's a vertical asymptote there, don't run across it to connect dots. Those vertical asymptotes act like boundaries, so you can't do that in that case. Now, let's look at one more example. Sketch the graph of y equals 2x squared minus 8x plus 6 divided by x squared minus x minus 6. First things first, let's factor both numerator and denominator and see what happens. And in the numerator, when you factor, you're going to have 2 times x minus 3 times x minus 1. And in the denominator, you'll have x plus 2 times x minus 3. Now, before you do any canceling, remember, the domain now, we know, is all the values of x except for -2 and +3. Those are the two values that would cause division by 0 in the denominator. And now you can cancel, and you see that you have an x minus 3 to cancel, so the function really looks like 2 times the quantity x minus 1 divided by x plus 2. Now you've canceled those x minus 3's, and that's fine. Just don't forget that x equals 3 is not in the domain. And there's one other thing that you need to remember now that you've canceled those x minus 3's. There is not a vertical asymptote at x equals 3. It's important for you to keep that in mind. However, something does happen at x equals 3 that you need to remember, and that is that you have an open circle wherever that graph goes at x equals 3, because you are not allowed to plug in x equals 3. And so here, since one term survived in the denominator, you will have one vertical asymptote. It will happen at x equals -2, and then at x equals 3, just remember that you need to have an open circle at the very end. Now, if you find the x-intercepts and the y-intercepts and the asymptotes, you can start plugging in some points and finish this up. The x-intercept is going to occur at 1, 0, and that's just from setting the numerator equal to 0 and solving for x. The y-intercept is going to occur at 0, -1. And remember, I got that from plugging x equals 0 into the function. In terms of vertical asymptotes, we already noted that x equals -2 is the only vertical asymptote. There's not a vertical asymptote at x equals 3. And the horizontal asymptote here is going to be found by keeping the 2x squared on the top, that's the dominant term on top, divided by the x squared on the bottom, that's the dominant term. And of course the x squareds will cancel in that ratio, and you'll just have 2. So the horizontal asymptote is at y equals 2. Now you can draw on the intercepts that we've already talked about. You can keep those asymptotes, both the vertical asymptote as well as the horizontal asymptote, in mind. And you can plot several points again, and there's nothing wrong with doing that as you go through. And then you're connecting those dots if you'd like. Just keep track of not crossing over that vertical asymptote when you connect those dots. And once you do all of that, the graph should look like this. Now, in this lesson, we've sketched a few graphs of rational functions basically from scratch. In our next lesson, I'd like to go back to some more traditional algebra topics that involve rational functions. You know, combining rational functions with the usual operations, including composition. I look forward to talking about that then.